logistics for those of us that aren't in the room and are just going to watch on YouTube. Review tomorrow, tentatively here, 6 p.m. We'll go as long as you need. And I gave you a little bit of a homework extension. It'll be due this coming Monday. So it's planned to be due on Friday, but you get the weekend to clean it up. Okay, back to the order statistic example. Let's just run this again one more time. What we are looking at is this problem. Okay, we are looking at this problem. F of x, where this is x over 2. It's not a uniform distribution. It might look like a uniform CDF, but this is a PDF, so this is the density function. I've been drawing this really not to scale very well, so you can see my areas were all off. I'll try to do just a little bit better. So this looks like this between 0 and 2. Right here, so x lives between 0 and 2. 1's in the middle, and it's still not to scale because we kind of know, well, maybe it's okay. This is a quarter, and this is 3/4. So that area. How did we get there? We just did some integrations. So f of x, the density dx between 0 and x is the cumulative distribution. Some people call this the measure. It's the thing that you integrate, or that's the thing that you end up moving x and it lives between 0 and 1. So that's technically the measure. So sometimes you can define the measure through the density, and not always. So if you ever take a measure theory class, they're gonna ignore that you can write down the density in a lot of cases and confuse you quite often by saying you're integrating with respect to the measure and you're not integrating with respect to the weights of the density. It really is the same thing. In our class, we'll try to keep everything Riemann so that we can always write down the density. There's a 1-to-1. But all that super mathematized stuff that you don't understand because they don't give you the density, you can kind of assume in your mind that maybe there's a density out there that you can think about. That's not always true, but for our examples it will be. So this thing right here is just integrate this. I can even integrate this. 0 to x. This is up my exponent by 1 divided by my new exponent. So that becomes 4 in the denominator. So that's the measure. We're going to use that to compute the probability of the jth order statistic. So I think in our example we wrote down the 5th order statistic that we wanted to understand. And we had to account for 2 scenarios. So whether or not the 5th biggest thing was less than 1, or the 6th biggest thing was less than 1. So, and it was just a consequence of ordering. So if the 6th biggest thing is less than 1, by definition, the 5th biggest thing is also less than 1, because the 6th biggest thing bounds everything. So there's a dependence there. So we had to compute 2 different scenarios. So our example was n was equal to 6, and the order statistic that we wanted to focus on, I'll call it the jth order statistic. I'm going to say j is 5, right there. So out of 6th thing, what's the biggest thing look like? What's its distribution? And we considered 2 different scenarios. So we looked at probability of 5 things less than 1, and we added this to the probability of 6 things less than 1. We'll write this down a little bit cleaner when we work through some more math. But that was the idea. So we had two probabilities where we redefined another random variable. I keep calling that random variable the number of things that are less than something. And what I mean by that is exactly that number of things. So I might not have said that exactly right last time, but I mean the exact number of things that are less than something. I called it 1. We'll change that variable to x in just a minute. So these two scenarios, in general, the CDF or the measure, the probability, all the same thing. The probability, if I wanted to look at the 4th order statistic, I would have to look over 3 things. I'd have to look at the probability of 4 things being less than something, probability of 5 things being less than something, probability of 6 things being less than something. If I wanted to look at the 3rd order statistic and understand its distribution, I'd need to look at the probability distribution of 3 things being less than something, or 4 things, because that bounds the 3rd thing, or 5 things, or 6 things. So I could have done this example with a lower order statistic, but our math would have been a little bit messier on the board. But the measure is always coming through this sum. So, and it's really just a binomial distribution that we're looking at. So if you're familiar with binomials and you're in the right class, this argument is relatively straightforward. But I'm going to slow down the argument, make sure we understand it. So basically the idea to understand order statistics is just the ordering of everything bounds everything, and we're just looking at all the different ways that we can come up with those different orderings. Okay, so just back to my code real quick. This was my probability distribution for our example, and I was asking the probability that the 5th order statistic in my code, and that's what I have here, right here, n is 6, our order statistic is 5, the probability was roughly 0.004. We kind of have some idea, because this is a Monte Carlo experiment, maybe we can't trust the 5. So we've seen that kind of bounce around a little bit, but it's really close to that. We know it's like 5 or 6 or 7 in that last decimal place. I have just a quick question. How many decimal places would you be inclined to look at in a typical Monte Carlo experiment? Just your own experience. I've seen this a lot of times where people report up to the like 12th decimal place. They're like, this is my number, boom. They report it. Is there any reason to do that? It's almost always wrong. So it's like 4 decimal places would be a lot. You know, you would have to crank the number of Monte Carlo replications very, very, very high, like millions, billions, to estimate something like the 7th decimal place or something. So unless you've ran your Monte Carlo experiment trillions of times, don't report all those decimal places. Report the ones that you're sure about.
There's some of them, I'm not sure if these are, I'm not sure if this factor I saw was actual Monte Carlo or a pseudo Monte Carlo method, but it reported error with, it reported the error with the result it gave.
Yeah. So possibly they did that in one of 2 ways. So they either ran the experiment over, maybe 3 different ways. They ran the experiment over and over and over again and actually looked at the empirical frequency of how often that number was in some epsilon, so some tolerance. They could have done that and given you an error. I would have appreciated that, because that would actually, I believe you. They could have used an asymptotic argument and said we're doing the central limit theorem and based everything off of the normal distribution, which might be okay, but sometimes normality isn't kicking in fast enough for that to be accurate. Or they did a Las Vegas sort of algorithm where they had a bound computed through a Chernoff bound. We will not cover this in this class, but there are bounding techniques where you can say up to some probability the error is in some range. So they probably did the first thing where they just ran it over and over and over. That's the one I like the most, the brute force one, because that's the one I kind of feel sure about. So I like theory, it gives me a guiding light, but I still like to check. So how well did it work in practice? And sometimes you'll be surprised. If you have problems with obvious boundary conditions, things get harder. So any asymptotics don't kick it up. So let me just give you a hypothetical question. We haven't really studied this. In a binomial experiment, if I were doing some sort of frequentist thing and using the central limit theorem, you've probably all seen this in Stat 101 type classes. If you've taken my Bayes class previously, you've done this experiment. If I were to estimate P and come up with a confidence interval, and maybe you can ask yourself, what does that mean? It's a frequentist technique, but I come up with a confidence interval where I look at P hat, it's X bar in a binomial experiment. If you don't know that, we will know that by the end of the class. If I add and subtract two standard errors, in our case, it's gonna be square root of P hat times 1 minus P hat divided by N. If this is too fast, we will cover all that stuff, but it is supposed to draw on your Stat 101 knowledge. But if I come up with the typical asymptotic confidence interval that they teach in a Stat 101S class, your early stat classes, if P was 0.01, true P, that's how I generated the data, how many samples do you think you would need before that confidence interval actually covered the true parameter with its nominal rate? So let's say I do 2 standard errors, 1.96 standard errors to be more exact. How many samples would I need before my confidence interval covered maybe between 94 and 96% of the time? So close to 95. I'm a rounder. Dylan?
Probably like millions.
Yeah, it's huge. It's heinous. It's probably more like 12,000. So, but if I ended up making that a little bit closer to the boundary, you get to the million pretty quickly. It's huge. It's not 31. So 31 works pretty good in the middle of the distribution. So it doesn't have uniform performance. So just what I'm going to try to tell you about is asymptotic methods, computational methods, Bayesian methods, and show you that they all have limitations and you need to check. And the only way you can really check anything is comparing things to each other. So that's going to be a premise for this course. Okay, there's something else I drew for you. This is the probability distribution of the 5th order statistic. So all I did here is I kept resampling 6 samples from that distribution that I wrote down, and then I reordered them, grabbed the 5th thing, and I plotted it in that histogram. So I used all of the data to reorder everything, but after I ordered it, I just looked at the 5th thing and I plotted it in that histogram. And so what we can see is the 5th order statistic tends to be greater than 1. That's where 1 is. That's where 2 is. So it's slammed up to the right of the distribution. And we kind of know that because we're placing more weight over to the right. So we would expect that large order statistics with respect to N would be over to the right. So, and we can kind of see that. So that's the distribution. So in my Monte Carlo experiment, I'm just counting how often we're less than 1. And it turns out it's a rather small number. Let's just change this so that we get a look and feel for what order statistics are all about. Let's look at some other order statistics, but I don't want to take all these derivatives and make this really nasty on the chalkboard, so I'm going to focus on the 5th one. The 6th one would be the easiest one to do, but it doesn't give you the full idea. Using the 1st order statistic, I could complement my way out or something like that, but the 2nd order statistic would give you problems, and I'd be on the chalkboard all afternoon. Let's do this one more time. Order statistic, order stat. Let's just look at let's say the 2nd order statistic. So the 2nd biggest thing out of 6 things, there's the distribution of that order statistic. That's the density approximately. It's not normalized, it's just a histogram, but the density function would look like this, something like that. Some smooth representation of that. 1 is here, and so the probability of the 2nd order statistic being less than 1 is it's highly probable. And there's a pretty accurate representation of what that probability is. If I were to come up with on the board the CDF of that, I would have to add together a bunch of different scenarios. Scenarios for the 2nd thing being less than 1, the 3rd thing being less than 1, the 4th thing being less than 1, the 5th thing being less than 1, and the 6th thing being less than 1. So that's the CDF. Any questions about this?
So
Sam?
could you not just complement that one, or could you not just like, let's say you're looking at the third order statistic, could you not just complement 1 and 2?
You could. But the third one probably wouldn't help you because n is 6.
Well, sure, right. So in the middle, like either
Yeah.
way, you're gonna have to.
Yeah,
for the-
exactly.
For the second one.
You can still use all those probability rules you've learned before. So yeah, sometimes you have to think about which way would make it less mathematical calculations. When you're computing on a computer, you want to do that for obvious reasons. It saves you time. And when you get a midterm exam question, you want to do the fastest way through the problem because it saves you time. So yes, definitely. So yeah, this probably would have been, I would probably use the complement if I were doing the second order statistic and look at the 0, 1, and 2 case because it would omit one of the terms. And I would have to take 1 minus that. Cool, good question. So that's what we're doing is we're trying to build up that PDF and see if we can write it all down. Let's just write this down one more time. Oh, I hate when they do this. So if you ever see your professors start to do this, go walk them up a nice piece of white chalk. They ruin the erasers for everybody for a week. Okay, so back to our example. What we wrote down last time we had our probability distribution, and I'm going to end up giving this some notation. So I ended up cutting down 1 in all of this, but I'm going to change this to x. So instead of using these probabilities 1/4 and 1 3/4, I'm going to end up using just this thing right here. So when I evaluated x at 1, that was 1/4, and those were the terms that were going into everything. So let's just write this down at first. So I want to be specific about what cap f that is, because this cap f for my order statistic is not that cap f right here. So this is the cap f for the x's themselves, the IID replicates. So I want to give this just a little bit different of a name, and I'm going to put down x5 right here. So this is my random variable that this is associated. I won't always do that, but when it's ambiguous, I'll try to do that. So this is the cumulative. For the 5th largest. And it's important to say that n is equal to 6. And so these were our 2 scenarios that we wrote down before. So this was going to be 6, choose 5. Different ways of reordering things. I'm going to address this in a second, exactly where that comes from. So, but this is going to be 1/4. So that's just fx of 1 is equal to x squared over 4 evaluated between 0 and 1. Now it's 1/4. I'm going to raise that to the 5th power. I'm going to have 1 minus 1/4 complementary probability. And that's going to be raised to the 1. Plus 6 choose 6, 1/4 to the 6th. 1 minus 1/4 to the, I'm going to say 6 minus 6. So this right here is going to be 6 minus 5. If you'd like. So where's all this stuff coming from? I just want to draw you a picture real quickly. So scenario 1, that's this term right here. I'm back to drawing this not in scale, but that's okay. So I think that there's 5 things that are to the left of 1. So 5 things. And then there's 1 thing over here. This is a bad analogy. It's not mathematically correct, but it gives you kind of an idea. of what we're actually doing. Let's just back this out and think about rolling dice for a second. And what we're doing when we're coming up with the total probability of something, or the cumulative probability of something, or the measure. If I wanted to know if I had 2 dice that I were rolling, we know how dice work. So they're labeled faces 1 through 6, it's discrete. I roll those 2 dice, and on each face is going to be a number between 1 and 6. And if I ask the probability, what's the probability of observing a 7, I'd have to account for all the different ways of seeing things. Seeing 1s and 6s, 2s and 5s, 3s and 4s. But it's not just enough to consider what if dice 1, if I put labels on them, wound up as a 3, and dice 2 wound up as a 4, that is a 7, so that would contribute to, if I were doing a Monte Carlo experiment, is a hit. It hit what I wanted. But I'd have to also account for if the dice faces were exchanged. So if they were flipped. So a 4 and a 3, and I'd have to add those into each other. So what I'm imagining here is infinitely sided dice, continuous infinite, with numbers that live between 0 and 2. Okay, so I can't really do that, but if you want to imagine some really faceted dice and take the limit, you're thinking what I'm thinking. And so what I'm thinking about is the probability of rolling dice and seeing these numbers, but I could exchange these in any order. So this could have been the first roll of the dice, and I got that number. This could be the second roll, this could be the third roll, this could be the fourth roll, this could be the fifth roll right here. Or it could have happened that that was the fifth roll, and this was the sixth roll. Or this could have been the sixth roll, and that's the first roll, and that's the second roll, and that's the third roll, and so on and so forth. So there's all kinds of different ways you can account for seeing those numbers. The reason that's wrong is the probability of seeing those exact numbers in a continuum is actually 0. But if we ended up making this dice really refined but discrete, you get the idea, and then take the limit of this. So that's where this is coming from. All the different ways that I could reorder the different labels on the actual eyes in the IID stuff. So that's where the 6 choose 5 ways. There's 5 ways that I can permute this, and I still have the exact same thing. How many ways can I permute that? There's only one way to permute that. So that's this number right here. So that's just 6 factorial over 5 factorial, 1 factorial. So I can reshuffle all of these numbers in 6 different ways. But then there's some orderings that are indistinguishable to me and I don't care about them. And so I can reorder those in 5 different ways. I just need them to the left of 1. There's only one way I can deal with that, right there. That's the 5 factorial orderings that I want to take out of everything. We're removing it by dividing because we build up the permutation by multiplying. So that's where this comes from. This is the other scenario, scenario 2, where I had 6 things over here. And there's only one way to reorder all that. So this is just 6 factorial over 6 factorial over 0 factorial, which is 1. So that's what that is. So those are just your binomial sort of ways of counting things. Pascal's triangle, if you know. Okay, so then I want to account for the actual probabilities. How many things did I see to the left of 1? So I saw 5 of them, I guess in scenario 1. These all happen with probability 1/4, so those are those probabilities. And the probability of that one other thing being in the complementary region is 3/4, and there was only 1 point over here. Following that exact same rationale, for 6 things being less than 1, we have that. I always like to write everything down, even though there's a lot of cancellation right here, just so I can see where the terms are coming from. So let's just change everything real quickly. See how this goes. No. Let's just change everything that I'm not just thinking about this one right here and coming up with numerical values. This is the beauty of math. So Monte Carlo experiment has a hard time doing this for all x's. You would have to run it for all the x's. So we can extend this rationale and we can think about f of x for the fifth order statistic is a function of x. This is just going to be 6, choose 5. F of x, which f, this original one right here. This is why it's important to distinguish the notation. So this is raised to the fifth power, 1 minus f of x. Random variables x raised to the 1 plus 6, choose 6. F of x raised to the 6. And I'll get rid of this one. So if you want, this was just 1. So we won't obfuscate the notation anymore. So that's our measure. We can only do this really for a one-dimensional experiment. Does it make sense to talk about the cumulative distribution of a bivariate function? Not really, because we don't know which way to add things up. So in one-dimensional stuff, everything is ordered for us. We add from the left to the right. That's just a convention. We could have done the right to the left, but we just didn't feel like it. I suppose if we lived in a different country, that could be an arbitrary convention that is picked up. Just like reading. Some people read left to right, some people read right to left, and I've seen people that read up and down.
If you integrate every dimension starting at minus infinity, so like...
You come up with that convention.
You would have, but it's a convention. But
Yeah,
it's
exactly.
one way.
You have to define it, and now there's lots of ways to define that. So you can even come through diagonal. So we don't even define that concept. So this is kind of a one-dimensional thing. So having the density is probably more important in multi-dimensions. And then you can integrate over the regions that you find important. So I like starting with the measure here. Let's just find the density. So the density function for x5. If you were looking at a textbook, they would probably bold that to tell you it's the random variable, it's the space in which the instances of the fifth order statistic live. So the density comes from just taking the derivative. And something magical happens when you do this, and I really love it. So it's f of x5. Just to be polite and tell us what the random variable is, it's a function of x, and I'm taking a derivative with respect to that x. So I'm just doing that. So I have to do the product rule. So I have to do a little bit of chain rule in doing this. So just watch me and keep me honest, make sure that I'm doing this correctly. So this is going to be, I'm going to take the derivative first of this term. So there's going to be 2 terms that are induced through the product rule. And then I'll take the derivative of this thing and add it in. So I always got annoyed in grad school when I didn't know when they were finished writing it. I'm like, you missed a term. Yeah, I haven't finished writing it all down. So those are the 3 things I'm going to do. So there will be 3 terms here. So derivative, 6, choose 5. I'll take the derivative of the first thing first. So this is going to be 5 f of x. Decrement by exponent. That's raised to the 4th power right there. I better do the chain rule on this. So that's little f. How did we get big F? We integrated it. When I take the derivative, I go back to the density function. And now I need to multiply by this thing. 1 minus f of x. This is raised to the 1. I guess I'll still write that down. Now I need to take the derivative of the second thing right here in the product rule. So this is going to be plus 6, choose 5. Multiply by the first thing. Take the derivative of the second thing. This is really just raised to the 1, so I'm just going to imagine it's not even there. And I'm just going to slide my derivative across this thing. So derivative of 1 is 0, but I have this negative sign I need to deal with. So I've got negative f of x. And I'll write it like that. So probably if I were doing everything more politely, I would change that to a negative like that. So now derivative of this thing. So plus 6 choose 6, 6 times f of x. A little bit of chain rule. Decrement my exponent. And that's what it is. That's the density. So beautiful thing happens is that there's two terms on the board that look exactly the same. Somebody said the last two, right? So this is 1 right here. This is a 6. This right here is just a 6 in these guys. So they look like the same thing. These are canceling right here. And all we're left with is this. That happens every single time. If I had worked through, let's say, the 4th order statistic and I had more derivatives, more chain rule, more product rule, everything on the board would cancel except for one term. You can try it out as many times as you would like until you finally convince yourself of that, or you could do induction in your mind. But I promise you, everything will cancel out except for one term right here. And that term is going to be the representation of that density function. Let's see if we can think about this conceptually. So this is our answer right here. I just have to go back in and plug in what little f is and what big F is. So let me just draw you a picture. Here's an illustration. This will give you a way that you can memorize this every single time, and you don't have to do this every single time. So I'm going to say some words that are a little bit incorrect, but they're close enough. So I'm going to talk about maybe I'm going to talk about this in general with the, I'll say the jth order statistic. So I'm going to say that it's here. So this is going to be the jth largest thing. So if I have some point, so I'm just focusing on the point that this is the jth largest thing, and I'm going to consider we have sample size n. That always changes everything. So what's big is relative to n. I know how many things are to the right of this. And I know how many things are to the left. Let me do the easy one. There's j minus 1 things over here. Because that's the jth largest, and I remove it. So I've got some number of points over here, and I'm saying that there's j minus 1. I guess we can kind of imagine the example. I'll make those 4, so you can think of that as 5. So, and then I have some number of things over here. How many things are here? N minus j. Very good. Very difficult to do at 9 o'clock in the morning is count. So n minus j things. It was 1 thing in our example, but I'll just write a few more of this down. So just as an arbitrary, I'll write some more numbers so that we can start focusing away from our example and get a little bit more general. So, quick question, how many different ways can I reorder these things? And they're indistinguishable. Not a trick question.
J minus 1 factorial.
J minus 1 factorial. N minus j factorial over here. There's only 1 thing right here. There's only 1 way to reorder it. What's the probability of being over in this region? Right here. I'm going to call this x, just so I can define it with some variable. We're focusing on the jth largest order statistics distribution. Let's give it a dummy argument and say what that jth largest thing is. I'll just call it x. So what's the probability of being to the left of x? Yeah. I'm going to write that down as x, right there. And so what's the probability of being over here? It's the following. So So how many things are here? It's j minus 1 things, so this has to happen j minus 1 times. The probability of being to the left of it has to occur a whole bunch of times, and then we have to deal with all the orderings. So based off of this picture, I can rederive what the density function looks like. I'm going to say something incorrectly. I'm going to talk about the probability of being at this point. But every time I say the probability of this point, what you're really thinking about is some small little ball around this, and I say the probability of being in that little radius. And then mentally, you're going to take this thing and you're going to map it down to 0 and take that radius to be 0. And you're going to move from probability to density function. So just like they did in calculus class. So, and I'll not really talk about the epsilon stuff. Sometimes you see people derive this first, the density function, and they'll do this sort of epsilon argument. So I like to start with the measure, take derivatives, and then explain it through a picture. So I've got all these different orderings. I can rearrange everything n factorial times. So I can take out all these other orderings in here. So this is going to be j minus 1 factorial orderings that are all indistinguishable to me. So I can reorder that j minus 1 factorial times, and I have the exact same picture. I've got 1 factorial if you would like. That's the number of rearrangements that I can do there. And I've got n minus j factorial rearrangements. And I have exactly the same picture. Again, all we're doing is accounting for the number of different ways those IID observations could have fallen to give me the same exact picture. Bless you. So now I just have to account for the probability of everything. Bless you again. So this probability right here, f of x, I'm going to raise that to the j minus 1 right here because I've got j minus 1 things happening with that probability. They were all independent of each other in the first place, so I just brought them together. I've got a couple more terms that I need to write down. I'll talk about this one right here because I can say the word probability. So here is the probability of being over here. I have n minus j things over there. So 1 minus f of x. So n minus j. And this is the part that I'll say wrong. The probability of being here, I'm going to call that little f of x. It's not a probability, it's the density. If you'd like to make this a really small interval and call it a probability, and you make your interval small enough, we will agree with each other. So again, this is a concept. So not the probability, but it acts just like a probability in terms of using it just in terms of the product. So this right here is the density function. So this is f of xj x. And the derivation is my picture. That's it. If you look at this right here, it's exactly this thing. So I have a measure. That's my j minus 1. J was 5 in this case. I've got just the density appearing. And then I've got the measure right here. N minus j was 1 in our case. These numbers right here, this part, can be expressed just like this. So I can either multiply 6 choose j times j, same exact thing, is this. Again, I like to just draw the picture and account for everything in the picture. Shall we do it for a joint order statistic? It's just as easy. So let me show you this part. Then next time we'll come back on Friday and we'll do that transformation of variables using our formula from the uniform example and plugging it into the joint order statistic thing. And then we have to do just one more step and do change variables transformation. Let's leave that. This is really fast. Joint order statistics. We're not going to use the same method to derive this by going through the cumulative, because there is no real cumulative unless we all agree on a convention. How do we add things? Multi-dimensional spaces just aren't ordered for us. That's what makes them hard to deal with. I don't always regret in elementary school they teach us about one-dimensional things, because everybody just gets sucked into thinking about what's the mean, the median, mode, why do they like all that, because you can order them. But in a lot of examples in real life, there is no best. There's best in different ways. So, it's too complicated of a thought. So joint order statistics. Here's my illustration. I'm going to talk about xi, and I'm going to say this is less than xj. So I'm going to look at the ith and jth order statistic, where I is less than j, or xi is less than xj. Ties don't change any of this. So sometimes in some classes you get ties, it changes the formula. Ties change nothing. So I'm going to say this is the ith largest. This is the jth largest. I'm going to give them some variable names, u and v. I think this is what they use in the book, so they can make me say things that I don't want to say. You'll see. So I've got some number of things over here. This is the easy one. There's I minus 1 things. With I minus 1 factorial reorderings. And the probability of being here is f from whatever my distribution is. I'll call it x or something like that. Same notation as before, of u. So because I define that to be the variable u. So this is not fu, this is fx of u. Okay, so that's what we have right here. Let's do the other one. This one is n minus j things. With n minus j factorial reorderings, and the probability of being in this region is going to be 1 minus f of v. We're only dealing with one distribution. We're not changing what that distribution is. And so it happens with this probability of being over here. So in this one, the probability measure is fv. I'll say f of x v minus f of x u. And I just have to wake up for a second and count how many things are in here. I'll give you a hint. It always adds up to n. So if you account for there being one thing here that I never write down, and one thing is here. So it's the remainder. How many things are here?
J minus I minus 1.
You're very good. J minus I minus 1. And you can see it pretty easily. That's the J thing, so this is J minus 1 things are over here, and I'm going to subtract off I things. So you could say J minus 1 minus I, or J minus I minus 1. I like the way you said it. So, and it has that many reorderings. J minus I minus 1 factorial. They do have this formula in the book that I'm going to write down, but you don't have to memorize it. All you have to do is think about the picture every single time. And now you can butter this up and build it up into 3-order statistics using the exact same thing. The hardest thing is just counting up how many things have to be in bins. So I'll write down my density function for xi and xj. I'll be polite and write down the random variable names. Again, I'd make those bold probably if I were writing a paper to tell you that's the random space that they live in, the definition of the random variable, not the actual instances. It's where it lives. But I like to be polite to tell you what the variables mean. So I'll call this u in v. Right there, and now I just need to go through all of this. So again, n factorial ways of permuting everything up here. I just look at all these and I subtract out the rearrangements that I find indistinguishable. I minus 1 factorial. I won't write in the 1 factorial. If you want to, you can. So j minus I minus 1 factorial ways of rearranging the stuff in the middle chunk, and then n minus j factorial. So if you added all these up, this would add up to n minus 2, and if you wanted to put in a 1 factorial, that's fine too. Now I just need to have all the probabilities in here. So probabilities when it comes to these points right here. So this is going to be f of x v, and this is going to be f of x u, the density function, not the probability. So this is going to be f of x. I'll be polite and write down the random variable raised to the I minus 1. So those things all landed there with those probabilities. And I have to just account for the rearrangements, which is this part. I've got f of x u. I've got the middle chunk, f of x v minus f of x u. I need to power this up to j minus I minus 1. I'll give you a hint. All of these terms in the exponents wind up down here in these denominators. I've got another density function evaluated at v, the argument. And then I've got this complementary probability evaluated at v. And this is raised to the n minus j. So yeah, I think you're doing the right thing. You're staring at the picture and making sure everything in the picture is accounted for in the formula. We're going to be using this regularly. The book seems to like order statistics to make the probability problems a little bit harder, to bring in problems with boundary conditions so that they can tell you more about inference later on in the book. Anybody have any questions about this? Kind of makes sense. You just have to put it all together. So I would say rewatch the video and see what we did to reconstruct that. We're going to come back to our example with the uniform and use this, plug everything into the formula so that we can see what that density is, and then we'll do some transformation of variables on it to come up with the probability distribution of the range and mid-range.
Shouldn't the first f of x in there be f of u?
Ah, you're right. Yeah, totally. What is x there? Was that the problem that everybody is staring at? Cool. Yeah, thank you very much. Yeah, just kind of chime in there if you know there was an obvious mistake. It does happen. Yeah, that's right. Very good. We'll come back next time, play around with this in terms of that triangular distribution. The transformation of variables is pretty straightforward. Understanding the bounds that creates those triangular edges that we simulated for the uniform example, that's exactly described in the book. So that part you might want to pay a little bit of attention. I'll derive that distribution next time, and then we're going to move into the central limit theorem. So I need the central limit theorem before we do the delta method. I probably should have told you about inverse CDF sampling this morning. I think I was going to tell you about that, how I actually simulated everything in my Monte Carlo experiment. So let's kick it off with inverse CDF next time. If I can remember and you can remember. And I start with that. It only takes 2 or 3 minutes. And then we're going to jump into the central limit theorem. And the preliminaries for understanding that are Taylor functions and moment generating functions. So we're going to need both of those. So you'll probably want to review those before we jump in. I'll give you a little primer and a review for 10 or 15 minutes on it, and then I'm going to assume that we're all refreshed with those classes. That will come up over and over and over again in this class, Taylor's and moment generating functions. So pull out your calculus book, see where all that stuff came from. We'll do it with the derivation in class. Keep it slow at first, but then we're going to be running with it.
Do you think it's allowed to say that the moment generating function is the Laplace transform?
I think it's not just fair, it's true.
Okay. I remember when I was in my original stat class, and
Yeah,
They didn't say it, but, you know,
it's true.
Yeah.
Yeah, so that thing you use the DIV class or something like that, or electrical engineers are pretty familiar with. The characteristic function is the Fourier transform as well.
Yeah.
We're not going to touch it in this class, but I don't mind talking about those things, how you extend a proof that you don't need to assume quite as many things. So the version of the proof I'm going to give you is probably the easiest version, but it coincides with the book's version. We can talk about bigger extensions, but this is something that will track you all through your academic careers. They're always, you'll get a book, it'll be more advanced, and they'll say, oh, we haven't covered it in a general case. That's reserved for more advanced textbooks. And it's like, when are we going to get to that more advanced textbook? So if you want to see the full-blown proof on the central limit theorem, people are still carving out theory on that. So, and the proofs could be rather extraordinary. We'll talk a little bit about the central limit theorem and convergence, how things converge, but I'm not going to test you on that. But I'll tell you a little bit about it. So that's all coming. Thanks, you guys. And again, I will give you those minutes back soon enough.